Okay. All right. Okay. So, continuity over an interval. So this sounds very, like, doesn't even really need to be said type of definition here. A function is continuous on an interval if the function is continuous at each point in the interval. Which, yeah, it's kind of like, of course, that has to be the case, right? So we will not really be proving so much that something is continuous. Like, we can't prove that as much. More, we're going to be looking to see if we see anything that contradicts the fact that it would be continuous. Looking for those points of discontinuity. Mm-hmm.
So this is what you were talking about earlier when you were talking about you just kind of have to know which one's continuous.
Yes, yes. So right here, our list, it's not every single thing, but it is many of them, although I need to put a condition right here. These types of functions, the following functions are continuous on all points, even though, what do I put in that blank? I think it's except something. Definitely.
What formula or whatever, like what expression that we know would be like not continuous? Because we kind of know all that.
I'll show you here in a second. I think what this is supposed to say is in their domain. So we need to know about the domains for these functions, and then we'll be able to tell if we're going to be continuous on that domain. So polynomial, this is something like f of x equals x to the third minus 4x plus 2. Basically anything that's just a string of x's and x squareds and all of that stuff. Domain for it is going to be negative infinity to positive infinity. Okay, or all real numbers for that. So polynomial functions are continuous everywhere. They do not have any discontinuities. Okay. Rational. This is like, I want to make sure I don't have this on the next slide. This is what I'm supposed to do on the next slide. Okay, here, hold on. Let's do this so we got room. I am going to, on this slide, I'm going to give you an example of what this looks like, because I know some of these we may not really know. A rational function is something like f of x equals x plus 4 over x squared minus 9. That would be a rational function. Really, it's anything with an x in the denominator. We'll talk about that domain in a second on the next slide, like I meant to. A power function is going to be like f of x equals x to the n power. And it may initially look like that is just a polynomial because you've got like x raised to a power. And if it is like x squared or x to the third or x to the fourth, it is just a type of polynomial. But n could be anything except for 0. So that means n could be something like, you could have something like y equals x to the 1/2. Okay? What is x to the 1/2? No, you're thinking of negative exponents, which is a different thing. Like that'd be x to the negative 2. It's like 1 over x squared. So that's although can power functions have negatives? That might also be a possibility for. Well, that's really irrational because you got an x in the bottom. It is the like square root of x, so that is a possibility there. Exponentials is going to be where you have a number like 3 3 raised to the x power. Your variable is in the exponent for those. Or another one we see a lot is like e to the x. That's a really common one. Let's write that one down. Right, those are our exponentials. Logarithmic are going to have some sort of log, right? So that could be like f of x equals log base 2 of x, or it could be the other one, like one that we see that's very common is natural log of x there. And then trig functions, I'm not going to list those out, but that's your sine, cosine, tangent, secant, cosecant, cotangent. So those are the ones that we're looking at there. So that gives you an example of what types of functions that we are looking at. Let's talk about the domains for each one of those. So I already started to get ahead of myself here. Polynomial functions, your domain is going to be negative infinity to positive infinity. With a rational, what kind of problems do you have with a domain for rational? You can have wholes or vertical asymptotes. Either one of those come from what issue with the equation? Zeros in the denominator. So the denominator cannot equal 0. So whatever your denominator is, it cannot equal 0. Power functions are typically going to be all real numbers, except when you have even radicals. So that is like a square root, a fourth root, a sixth root, dot, dot, dot. Right. If you have an even numbered radical, then what we call the radicand. Is that a D on the end of it? That D may or may not be there. It has to be greater than or equal to 0. You can't have a negative underneath the square root. They definitely use a D on the end of that on that website. Let's see. Yeah, it looks like it does have a D. Looks like if you do it without a D, it's a plant. Okay. For exponentials, your domain for those is always negative infinity to infinity. So exponentials do not have any discontinuity. Sometimes they look like they do, because when you graph an exponential, it starts off growing really slowly and then it shoots up really fast. So sometimes it looks like it's got a vertical asymptote because it's going up so quickly, but it does not. It continues to increase forever. A log function, though, I do not know the name for what you're taking the log of. I don't know if it has a name like radicand is what you're taking the root of. I don't know if there's a name for this. So, the expression inside the log has to be greater than 0. It cannot equal 0. And then for our trig ones, there are some of them that are all real numbers. Which ones? Sine and cosine. So sine and cosine are going to be negative infinity to positive infinity. Those are continuous everywhere. I really don't want to like list all of these out because for the trig functions they're repetitive. They go, they'll have vertical asymptotes, spaced out at different intervals. So I'm just going to say that tangent, cotangent, secant, and cosecant have vertical asymptotes. No, it is not. CSC. Sorry about that. Okay, so they're going to have repetitive vertical asymptotes for those. Okay, questions? So a lot of these, like we've kind of built up, you should have like learned all of these along the way. We didn't really do power functions much, but I think we pretty much went over all of these in pre-cal. We looked at all those types of functions. We definitely looked at logs and exponentials. We did trig. We did polynomials because we had to do that factoring and stuff. So actually, no. That's math 3. Did we do polynomials in pre-cal? Can't remember. I'd have to go back and look. I've not taught it enough times that way to remember. You definitely do it in math 3 for sure. Rational we definitely did because that's where we were looking for holes and asymptotes that we were just talking about a couple days ago. We are supposed to, for example 1, show that f of x is continuous on the interval from from 2 to infinity. Okay, so what are your ideas? How can we show that these we're going to have to like write things out here to prove that this is continuous on this interval?
Well, plug in 2 x.
Okay.
So that is the limit of.
Okay, I agree for that at 2, for sure. So like we plug in 2, we'll get 1. So that limit and the value of f exists. It definitely exists there. But that only proves 2. Does that prove 3? Or 4? Or 5? Or 6 or 7 or 8 or 9 or 10? Are we going to be able to prove it at every point? We are not going to be able to prove it at every point because we would have to spend the rest of our lives doing so if we tried, right? Like we would never find a spot where between 2 and infinity where this was not continuous, but we can't prove it point by point because there's just infinite points in that interval. So, and even if it was a closed interval, even if it was just from like 2 to 3, there's still infinite points between 2 and 3 because you've got 2.1 and 2.01 and 2.001 and 2.0001. So there's still infinite points even on a closed interval. So rather than being able to show like at every point that this is continuous, we need to think about the type of function we have and where the discontinuities are. Okay? So what type of function is this when I've got 1 over x minus 1? It is rational. And on our earlier slides, we said rational functions are continuous on their domain, right? What is the domain? Or well, let's say, what's the only number that's not in the domain for this? 1 minus 1 would give you 0. You got 0 in the denominator. So that's where we have a discontinuity. We got to have a vertical asymptote at x equals 1. So we would say that f of x is a rational function that, and therefore is continuous at all points except x equals 1. Now, does it matter for our question that this function is not continuous at x equals 1? It does not, because our interval is from 2 to infinity, which does not include 1. And so, since x equals 1 is not on the interval to infinity, f of x is continuous on that interval. So essentially we're saying we know these functions are continuous except for these points. That point's not on this interval, so it's continuous everywhere else. Okay, questions? Okay, let's look at some of the other stuff that we'll have. So for example 2, the graph is made up of a line, segment, a point, and a part of a parabola. Let's see, hold on. Why is it not letting me? There we go. Okay. Is g of x continuous on the interval from 4 to 8? Why? That probably should say why or why not if I was better at writing problems. So from 4 to 8, are we continuous? Okay, so 4 is right here to 8 is right here, and our function is continuous on that interval. Yes, because parabolas are continuous. And that's all you have on this interval. However, what about if they ask us from -2 over here all the way up to 8? No. Where do we have a discontinuity? At 3. So we would say no, because g of x has a discontinuity at x equals 3, because, okay, so we need to explain why. Okay, so we could say there's a hole, but I would like for us to use some of that like language we were using for proving continuity.
The removable is continuity because g of 3 does not.
Does g of 3 exist?
Yes, because there's no 1.
Because you got the dot. Does the limit exist at 3? The limit does exist. What is it, Webb?
G3 is not equal to the limit of x approaches 3.
Very good. The g of 3 is not equal to the limit as x approaches 3 of g of x. So our limit would be down here at the open circle. and our value of the function, our g of 3, is up here at the colored in circle, and those don't match, right? So that tells us that we're not continuous there. You'll see, I think in some of your like questions that you're going to get tonight, it'll be asking you for a reason. It was kind of doing that last night as well, asking you for that reason. So in this case where you've got a limit and you've got a value, but you just don't have those equal to each other, this is sort of what you would write here. Okay, questions on that? All right, let's keep going. Okay, this asks us is f of g of x continuous on the interval from negative infinity to infinity. So we're going to, first of all, have to find f of g of x, and then we're going to have to think about that continuity. Really what we're kind of trying to find are there any discontinuities? Because if there are any discontinuities, then the answer is no, right? We have, and I guess I probably should have put earlier, we've got a rational function and a square root function, both of which are continuous. So the composition of continuous functions is also continuous, but it's only on the certain domains of those functions. So if we have f of g of x, okay, that is going to be 1 over x, or square root of x plus 2 minus 5. So, can somebody think of a point that would make that discontinuous? Yeah, any point that would make it not continuous. 23? Okay, so at 23, you would get 1 over the square root of 23 plus 2 minus 5. That would be 1 over the square root of 25 minus 5. That would be 1 over 5 minus 5, which is 0, right? Discontinuous there. So if I try f of g of 23, this is what I get. Therefore, f of g of x is not continuous at x equals 23. Therefore, f of g of x is not continuous on negative infinity to infinity. So I just need 1 point, and then it's false, right? There's other numbers that I could have used. Does anybody know another number besides 23 that would make this false? There's actually very many of them. Numbers that will give you imaginary numbers. So what's something that would give me an imaginary number? -3, or -4, or -5, or -6. Anything that would give you a negative underneath that square root. So I could have said the same thing, but instead of using 23, I could have used -3 or -4. All you need in this for this particular problem is one single point that would make it false, and then you can say it's false for that. Okay, does that make sense? Questions? Okay. All right, so now we have to talk about the intervals on which this function is continuous. So we've got a rational, which is going to be continuous everywhere except for where the denominator equals 0. And then this is really just a point right here. So, for this, we're really looking to see if the limit exists at this point and if it matches f of 3. And if it does, then it's going to be continuous everywhere. If it does not, we're going to have a discontinuity that we'll throw in there. So So what we would need to do is we need to do the limit as x approaches 3 of f of x. Now, in this case, notice I didn't do left and right in this case because I don't really have like a less than greater than scenario, right? I use this equation everywhere except for this one single point. So really I can just do the limit from both sides here. This isn't a like left side, right side scenario. So I would just do the limit as x approaches 3 of, I'm going to go ahead and factor this. Is that all right with you guys? X plus 3, x minus 3 there in the top over x minus 3. And then my x minus 3's are going to cancel, and I will get 3 plus 3, which will give me 6. However, what is f of 3? That is 3. And so the limit as x approaches 3 of f of x does not equal f of 3. So f is not continuous at x equals 3. But this particular problem wanted me to tell where it is continuous, not where it's discontinuous, right? So I would say f is continuous everywhere else. It's a rational function. It's going to be continuous everywhere else. So I would say on negative infinity up to 3, and then 3 to infinity if I want to use interval notation. Or I could say for x is not equal to 3. Or I could say for x is less than 3 or x is greater than 3. So just those are like 3 different options of how to write the places where this is continuous. You might see any of those given. It just depends on what notation they're wanting to use there. Okay. Questions there? I do not know why I have a blank page there. I don't know if you guys have it. You guys don't have one. You know what? Now right here on my little thumbnail, I've got an equation. Right here I got nothing. Okay. Alright. What, I guess, can I see yours real quick, babe? I'm going to put what we've got here. We got f of x equals e to the x, or x is less than or equal to negative 1. We got x to the third plus 2x. For negative 1 less than x less than or equal to 0. We got 5x over x minus 2 for 0 less than x less than or equal to 4. And we got cosine of 3x. Okay, so, oh, what was that last condition?
Greater than 4.
Greater than 4. Okay, all right, so I want to know what intervals this is continuous for. What I really need to know is where it's discontinuous, and I'm going to list everything else. So all of these functions, exponential is continuous everywhere. This is a polynomial. It's continuous everywhere. Cosine is continuous everywhere. Now, this one is a rational. It does have a discontinuity. What is that discontinuity? X equals 2. So x cannot equal 2, and that falls between 0 and 4. So we have to continue. We have to oh gosh. So I'm going to make me a list of my discontinuities. Then we can write about where it's continuous. So x cannot equal 2. The other thing I have to check is whether or not my piecewise pieces match up, right? So if you were doing this on like a free response question, you would need to do the limit as x approaches -1 from the left of f of x, which is the limit as x approaches -1 from the left of e to the x, which would be e to the first power, which is just e for that. Now, I would also need to do the limit as x approaches -1 from the right of f of x. Oh, I'm sorry, it is -1, and that would be, what would that be? 1 over e. Thank you. And that would be, here we got to do the limit as x approaches -1 from the right of x to the third plus 2x. That is going to be -1 cubed plus 2 times -1, which will be -1 minus 2, which will give me -3. Does my limit exist at -1? It does not, because 1 over e does not equal -3, right? So x cannot equal -1. Can't have that one. Now, if it is a free response question, then you technically should do limit notation for all of these. However, if it is a multiple choice question, is the limit notation really necessary? We're thinking limits, but we don't necessarily have to write the whole thing down because it takes a while, right? So for 0, I would plug into the second and the third equation. So if I do 0 cubed plus 2 times 0, I would get 0. So that would be my limit as x approaches 0 from the left. And then for the other, I would do 5 times 0 over x minus 2, or 0 minus 2. That will give me 0 over -2, also equals 0. Does my limit exist there? Do I have at least one or equal to sign? I do. So it's continuous at 0, right? So I don't have to include that in my discontinuities. Then I want to check 4. So I would do 5 times 4 over 4 minus 2. That's going to give me 20 over 2, which will be 10. And I don't even really have to do the last part. If I do cosine of something, am I going to get 10? What's the biggest number I'm going to get if I do cosine of something? 1. That highest number you have on your unit circle is 1, right? So I am going to have a discontinuity at 4. So you are probably going to see this written like this. Will be continuous on -infinity up to -1, and then -1 to 2, 2 to 4, and then 4 to infinity. We use parentheses with everything because those are not included. Okay. Questions? Okay. Homework tonight is on